Today we will see the third chapter, that is motion in a plane. What do we mean by motion? In physics, this is an important concept, important thing. Why? It's been moving. Okay, in physics, in nature, nothing is at rest. Everything is moving. Okay, what even you are moving while you are sleeping also, correct? Because on Earth is spinning, so everything is moving. Okay, so there is nothing like a absolute rest. Okay, so that's what. So in physics, everything in universe, everything moves. Okay, nothing is idle, stationary. Okay, so that means everything is moving. So that's where that move. When we represent that movement in the physics, we call that as a motion. What is the change in position with respect to time? Okay, so means any object or any matter or anything, if it keeps changing its position in time, then you call that as object is in motion. Okay, for example, when you kick a ball, the ball is moving at different instants, the ball is at different position, right? So that's the motion. So a ball, when you kick a ball, the ball goes up like this and goes and falls, right? So the ball is in motion. Drop a stone, stone is in motion. Okay, and well, you have many things also. What else you can give me example? Atoms are also in motion. Everything, electrons are moving. If you say the matter, all the electrons are subatomic particles. They all are in motion. Okay, and the universe also. Earth is moving. The planets are moving. Okay, the sun is moving. Galaxy or Milky Galaxy itself is moving. Okay, everything is in motion. So, and motion means what? Change in the position of an object with time. Okay, so that is what we call as your motion. Okay, so this is simple. Now, when we say motion, means, but okay, so I had defined. So motion means what? Any change in position of the object is called as your time. Now I ask you, are all motions similar? No, right? When you kick a ball, it makes a parabolic, means it makes a arc like this and fall. It rises in the air and then goes and falls down, right? You drop a stone, it has a different type of path. Okay, and otherwise you tie a stone on a rope and whirl around. The stone has a different type of motion. Okay, or when you give that spin shot in a football, so the ball goes like this. Correct? So, and that has a different type of motion. Okay, and there are many things are there. Many things are there, but you find they all are different type. Okay, because you see the stone falls, it falls vertically down. When you kick a ball, the ball straight away goes and falls. Makes an arc and go and fall there. When you spin a stone tied with a rope, that makes a circular orbit. Okay, and that's why when you kick a ball, when it makes a turn or something like that, what other things you have? Some spiral motion kind of. You have the water sprinkler in the garden. Okay, the water coming out. If you traject the water of the path, the water won't make a straight line or something. It makes some different path. Am I right? So what we see in physics, everybody in universe, everything is in motion, and not just they're all motion, but you find the motion has a different. There is some difference between the different type of motions. Okay, so then we have to classify type of motion. Okay, so one motion is simple. When I drop any stone, it falls, it makes an arc and fall. Will it make arc and fall? I'm just dropping a stone. It makes a straight line. Okay. I'm rolling a ball. Okay, got it. I'm rolling a ball. Will the ball make a circle? No, the ball moves straight. Okay. And there are many times, okay, you have the car, you made the pullback car, the toy car. You pull back and leave it. It goes straight. There are many things. In those cases, what happens? So when it is a straight line, when the motion is along a straight line, then what? It's what you call as then you call that as your rectilinear motion. What is the rectilinear motion? Motion along a, tell me? Yes, along a straight line. So that is what you call as a rectilinear motion. When the motion is along a straight line, you can represent that motion. It's a straight line, na? So it can represent as only one axis, one line. Am I right? It's not going to make how many dimensions you want. You want to just say they're all in a straight line, right? Suppose, okay, so for example, what happened? I'm okay. Let us take out let us try to draw the motion along a straight rectilinear motion. Okay, so to define this position at different instant, this all will fall on a line. Am I right? So if you want to, in a graph, if you want to represent, all you need is only one axis. It's either x-axis or y-axis. It's going to follow along the x-axis or y-axis. So it's what you call, you have only, how many quantities are represent to the point in that line? One quantity. Okay, therefore it's a one dimension. This is one dimension motion. So rectilinear is basically one dimension motion. Okay. And now I could ask you, suppose that means if every object is moving on a straight line, will one dimensional motion be, one dimension is sufficient? No, because they are not going to move on the same direction. They all are moving on a straight line, but they can have a different directions. Okay. So when you different directions, okay, let us come to that later on. Okay. So when you're dealing with only one object, when it is moving along a straight line, and if I make sure that body will not move out of the straight line, then that whole problem is what? I can deal it in one dimension. Okay, so that was called as your rectilinear motion. The example is dropping a stone. Okay, when it is a one dimension, the vector will have only two directions, either downwards or the upwards. Okay, you may say, why do I need a vector there? I can write expresses plus x and minus x. Okay, but no, we need a vector because even when you want to do for a collection of objects, or when you want to go for a movement in another higher dimensions, which I'll tell you in a short while. Okay, so for that you need a vector. So it's better to represent the vector notation even for a rectilinear motion. Okay, because if you want to deal with 2-3 rectilinear motions, then naturally then it won't be on a straight line, there are multiple dimensions will come. Okay, so this is what you call as a rectilinear motion, and there's a motion along a straight line. A simple example is you are dropping a stone. And if you remember all the equations of motion, what you studied in your, I think 9th and 10th standard, they all are actually rectilinear motion. Because you are dropping a stone, it deals with only one direction on a line. Okay, so we will see when it is 2-dimensional how it happens. Now this is a one type of motion, we see it in the day-to-day life. Okay, so one is the rectilinear motion. The another motion is what we call as a motion in a plane. Okay, or you can call it a planar motion or motion in a plane. What do we mean by motion in a plane? As I told you, you kick the ball. Okay, you kick the ball made an arc and went and fall. If you want to define the whole thing, will they all fall on a single plane?
No.
Why?
Oh, single plane.
Yes. Am I right? I can put a plane there. So I can, okay, so if I, okay, the point is you take a line of infinite line and stack the line along the orbits. So it will form a plane. Am I right? So what am I saying? So if you see, this is the path of the ball, okay, and if you draw vertical lines along this one, these lines will form a plane. You got it? This line won't make a curve like this. If it is a curve, then it is not a plane. Okay, it is a curved plane. Okay, it will be just a simple plane. They all will fall in a plane. Okay, so similarly, there are many things. Even a circle. When you tie a stone in a rope and you whirl it, the circle will be what? It will be on some plane only. Am I right? Even though if you make it a tilted one, still it will be a plane. Okay, always this is going to be in a plane. Okay, so that is another type of motion. So there it is not a straight line, it's all going to be in a plane. Okay, so that is the one type of motion which we call as a motion in a plane. Okay, so for that, here what happened for rectilinear motion, you need only one axis, maybe x axis plus x and minus x. Simply in your 10th or 9th standard you have this number line. So number line is nothing but a one dimension. In a number line, I can represent the rectilinear motion. When it comes to motion in a plane, that is not sufficient. It's going to happen in a plane. So then what do we want to use? Tell me. X and y axis is a two dimension. So then I have to make this x and y, and if you are kicking a ball and then the ball will fall on this xy plane, I can do this. Okay, or on the other hand, if you are whirling around a stone, that can be made as a circle. Okay, around the origin or wherever you can take. I just plot it around the origin here. Okay, so this is something what we call as a motion in a plane. Okay, and then comes the last one, motion in space. Okay, so that means what? The motion which cannot be represented by a single plane. Okay, so what is that? Let us write out motion in space. See, motion in space, even a rectilinear motion can be having a motion in a space, as I told you. If there are, okay, you are making sure all the objects are moving in a straight line. But now, the directions are different. If I deal with a single object, then I can have a rectilinear motion, I can use this one dimension line. Now, if you want to deal with the many objects, then of course, they are now going to different direction. You can't say everyone is on the plane also. They can have any possible directions. Suppose, for example, bursting a cracker. You burst. All the particles are thrown away. Okay, from the center, the cracker is burst and all the particles are thrown out. They all are moving in a straight line. They are not going to make a move straight line, go and fall. But initial region, you can say they all are moving in a straight line. Correct? So you can say, you take up a particle. So that particle can basically, initially you can define it as a rectilinear motion. If you take a longer, it goes and falls down. Then it is a motion in a plane. Okay, so if I track only one particle which came out of the cracker, then you can make either a rectilinear motion, initial short period, or a motion in a plane. If you want to see the whole cracker, you got it? Then that is not on a single plane. It's over all possible directions. There you get the motion in space. Okay, so there may be other thing also. Now, we can very simple also. I said, okay, I used to give the example in the beginning itself. You give a kick. What is that kick they got? That football, side kick or something. You got it? What happened when you make a kick? The ball, it spins, correct? And the spin will give a drag and the ball make a circle. Okay, there the ball may not be able to, the way the ball goes off. See, what happened? You kick the ball, So the ball goes like this and then falls like this. Okay, it may not be able to represent in a line, neither a plane. Okay, so that is what we call as when such thing happens, then then that problem is a motion in a plane. Okay, for example, a simple example, you see the billiards boards or the carom board. All the particles are moving when you hit it, they are going to straight line, rectilinear motion. Okay, but can you deal the whole problem of the carom board in a rectilinear motion? No. Even though you take a single coin, it hit the wall and come back. Hit the edge of the board and reflect back. Am I right? So then once it reflects back, then it is no more rectilinear. It became a planar. So there, even though you add up all the coins are going, even though you hit, will they run out of space here and there? No, they all will be in the board itself. So that problem, the whole problem is a two-dimensional problem in a plane. Okay. On the other hand, if you take it in a space, you remember there is in the fun land and there are a lot of balloons will be there. You go and jump and people throw it around and all. Okay, so those regions, it's a space, full space. It's a three-dimensional motion. Okay, every body is having all possible directions. So, and these are the examples of your motion in a plane and motion in a space and the rectilinear motion. Well, so till 10th standard, I think whatever you studied mostly is a rectilinear motion. All your equations of motions, everything, they are rectilinear motions because you don't throw a stone, because if you're throwing a stone, then it will be punished by your principal. So you can only drop the stone. Okay, which makes your equations of, then you get their equations of motion. Okay, so that's what we saw. But in this 11th standard, we were not going to deal with only the rectilinear motion. We will deal with the motion in a plane. Okay, motion in space, I don't think so you have it. Okay, but that's a more probably, I don't know, in 12th standard also I don't think so you have it. You have only the motion in a plane only. That's a two-dimensional problem. Okay. Fine. And okay, as I said, when the motion, rectilinear motion, I am going to deal only one object. You don't need the vector notation. You either take plus x or minus x. Okay, you can do the whole problem without vector notation also. But still we use it as a vector notation. The reason is, mostly we will dealing all the problem to be in a plane. So when you define the problem with the proper vector notation for rectilinear problem, then to get back to the problem to find the motion in a plane, that makes it easier because I already introduced a vector notation. Okay, so that's why we'll use a vector notation. Okay, so first today we will see about this rectilinear motion and we will use vector form, vector symbols. Okay. Okay. Fine. So in rectilinear motion, all what you will do is you can define the motion on a single axis, correct? So you call it a number line or whatever. So it is origin. I may call it as plus x and minus x. Or if you don't like it, you call it plus y and minus y. It doesn't matter. It's only one dimension. Okay. So in rectilinear motion, what happens? So okay. So then we will try to define certain physical quantities. So what we are going in a rectilinear motion, you are going to drop a stone or something. It's going to fall on a straight line. At different time, you are going to fall on a straight line. So now you drop it, I catch. Okay, someone from the top they dropped and I caught the ball. The ball is being dropped, so it's a rectilinear motion, but it stopped. I hold it for some time and then I drop it. Okay, and then I can also the ball came up, I caught the ball, I throw again vertically upwards, then I drop it. Okay, so you can see the different situations, right? One is the ball straight away dropped, it went and fall. Another case, the ball came up, I hold it and then I dropped. The third case, I hold the ball, I throw it up, it again went up and then the ball. So when I see it in different times, these three processes are going to have different equations. Okay, different ways this ball motions are there. So then what happens? So let us try to deal this whole problem in one dimension like this. Okay, so let us say, we are dropping the ball. Let the ball be dropped from, say, okay, 0. Okay, I am going to drop when the ball straight away falls. This is the ground. Let us call this as maybe at what distance? Say, let us say 5. Okay, so then we can define the time taken, maybe say some t. There are many times happen. Okay, so let us see those time later on. So now, so at different time, the body is going to be on different locations. Am I right? When I first drop the ball, it straight go and fall down. In the second case, in another case, what I did? So this will happen at certain time, say t1 or something, whatever. Okay, certain time, sometime. I'm not going to mention the time. Time let us see later on. Okay, the second case, what happened? I dropped the ball. The ball was coming. I stopped it in between for some time and then I left it. The third case, what happened? I dropped the ball. So the ball was dropped. I caught the ball, throw back again here, and then it again went and hit the ground. Correct? These are the 3 cases. So now, so in 3 cases, what you see is the distance traveled. Okay? Effectively, all these balls have traveled the same distance 0 to 5. That is 5. But it is not true. This ball has also moved the same distance, but the time taken was longer. But whereas this ball, it's traveled a longer path. You got it? The time is also different. The path is also different.
So the direction also changed at one point.
Pardon?
Direction as well changed at one point.
Yes, direction also got changed at one point. Okay. So even though when I say the end result, suppose I am going about here and here, the end things are all same, but individually the trajectory of the ball is different. It's all because I take 2 cases, the ball I dropped vertically down. Second case I dropped, caught the ball, then I dropped. Third case I caught the ball, threw vertically upward again, and then I dropped. So I represent these 3 cases. So now let us see. So now I have to define some quantity based on that. So what am I going to do? I have 2 quantities I am going to define. One is your displacement. And second is your path length. From the name itself, you can find out what is the meaning of it. Let us see first what we mean by displacement. Okay, what the displacement is. Okay, so let me remove these cases. Okay, so I'm going to remove these cases. So let us say, so I'm going to drop the ball. Okay, initially it was at certain x1 and finally it reached certain x2. Okay, so I'm not going to make it as an origin here. So let me call this as this position, the initial position, let it be x1 and x2. Okay, so and this at the time the ball the ball at x1, the time is t1. When I left the ball, when it reached the ground, the time is t2. Okay, so then when I say x1, so x1 is a vector. You can have a vector, you remember? Suppose if this is the origin, for example, if this is the origin. So this is a vector. Am I right? Oh, sorry, I draw it. So this is one vector and this is another vector. Am I right? So for example, if you do it in 2 dimension, if you remember. So if I have a point x1 here, x1, comma, y1. You remember, I think I showed you, right? x1, y1? x1 and y1. So this is a vector. Am I right? Similarly, other point x2, comma y2. This is another vector. Correct? So, same way, if this is the origin, though it is one dimension, I can still define a vector. Am I right? So, this is the one vector x1 and this is another vector x2. So, displacement is the difference between these two vectors. That's what x2 vector minus x1 vector is called as your displacement, and this symbol is something like S, or you can write as delta x vector. Okay, so the displacement means what? The difference between the initial and the final position vectors. Okay, so position vector, difference between the position vector. That's what your displacement is. Okay, so what we write the displacement? Displacement as vector equal to delta x vector, that will be x2 vector minus x1 vector. Okay, so this is what we call as a displacement. Okay, and they give an example, like for example, then the vector you can define a magnitude also. Magnitude is nothing but the length of it. Am I right? The length of it. So now suppose if I say x1 is 1 and x2 is 2. So what is the magnitude of the displacement? 1, because it's 2 minus 1, right? This is 2, this is 1. If it is 4 and this is 1, the magnitude will be 3. Okay, so this is what? So this can be positive x direction as well as the negative x direction also. Okay, if I means I represented as this is positive x axis. Someone may not like it. You will say let me choose as a negative x axis. That means for him the ball going from here to here. So x vector. Okay, or the same way you can throw up the ball. That time it is a negative x vector. Okay, so this is what your displacement means. So displacement is a scalar quantity or vector quantity? Vector quantity, because the difference between two vectors. Am I right? You remember we did that. Okay, only when you have a product you can have scalar product and a vector product. But addition and all you normally get a vector only. The resultant will be a vector. Okay, the triangle of addition, parallelogram and all you saw. Okay, so displacement is a vector. And now the path length is simple. Path length, I told you. Now for path length, let us come back to our old discussion. So path length says what is the what will be the dimension of the displacement? Can you tell me?
Two dimension.
No, dimensional analysis. That dimension.
Displacement D1.
D. What we call the dimensions? What are the dimensions?
So
length.
L1.
Yeah. So dimension of displacement will be, you should remember always a dimension. Okay. For displacement dimension will be L1, M0 and T0. This will be the dimension of it. Okay. So now let us come back to this path length. Path length is what is the actual distance it has travelled. Okay, it is not between the difference between the initial and the final position vector. Okay, so what I said, the ball went from x1 to x2. Now let us go back to the story I said. I am not going to do that. Okay, let us take the third case. The ball, it went here, I caught the ball, then I throw ball up and then it went up here. So now, the displacement, the path length is not just x2 minus x1. You got it? So x2 minus x1 is a vector, but here it is not. The direction goes off. Okay. So there what happened? Your path length, suppose what I am going to call this as 1, and if this say something around 4, and if I call this one as say, what do you want to say? 3, and this region as 2. So then what is the distance it actually travelled? Total length travelled is? Okay, 1 to 3, that is 2, plus 1, correct? Plus 1, plus 2.
2 to 4.
Correct. So what happened? First it travelled up to distance 3, plus, then it travelled the distance upward by 1, correct? And then it went back to 4. Correct? 2 to 4. That makes it 2. So total length traveled, distance traveled is what?
6.
6. Okay, so this is not, even though he said 1 and 4, the effective distance what traveled is 3, but since you made the body to move up and down, so it does eventually, so this is what we call as a path length. Okay, so there are some examples what they given in your book. So if you want to see, and what will be the dimension of the path length? Tell me.
D1, L1.
Correct. Same as displacement. Okay. So, and what they say is, if for example, then if objects travel along the x-axis from x equal to 2. Okay, let us give the problem what they are doing it. Okay. So what I'm going to explain what the written in the book itself. Okay, so that will be easier when you read. Now you can connect it. So let us what they say something. So for x is equal to, they say if an object travels along the x-axis from x equal to 2 to x equal to 5. This is x equal to 2 to x equal to 5. See, if you want to draw the y-axis, you can draw y-axis also. I didn't draw because it's in one dimension. Okay, but you should remember always there has to be y-axis also. That's why we are writing it as a vector form. Okay, in a 2D plane, when you take a plane, this all becomes in the plane. So you start representing the vector in the linear itself, rectilinear motion itself, so that easily you can do it for your motion in plane also. Yeah, okay, fine. Tell me. So it starts from x equal to 2 to x equal to 5. Then the distance traveled is 3 meter. Am I right? So they're putting it in meter, 2 meter and 5 meter. So the distance traveled is 3 meter. Cool, because this is a distance difference, right? 3 meter. In this case, the displacement is also 3 meter. Am I right? It has traveled the same distance. As I told you, I dropped the ball. The distance traveled, it's a 2 meter, and when it goes to 5, distance is how much? 3. Your displacement as well as the path length, they both are same. I am not catching the ball or anyway, I am not stopping it, just a motion. So this is a case where displacement and your path length are equal. Okay, and now they come. Now you say, however, if the object now comes back to 4, so what happened? The object went up to 5, now it's coming back to 4. Okay? Then the distance through which the object has moved increases by 3 plus 1. Am I right? Now the path length is basically what? 3 plus 1. 4. Okay. Its initial position was, now if I say, so what is the displacement now? Suppose it starts with 2. Okay. And the final position, I put this as a final position. Okay. So now if I call it what happened? Okay, the point is something like, I dropped the ball, it hit the ground, bounced back and stopped there. Okay, you got, that's what, like, it goes up to 5, bounces back and stops there. Now what is the displacement? Initial vector, the final vector. So that will be what? 2. Okay, so that's what. So this can be bounced back. But here the path length is longer. Correct? That's what they have written. 6, yes. So however, if the object now comes back x equal to 4, then the distance through which the object moved 1, its initial position was 2 and the final position is now 4. And thus the displacement is 2. Correct? The magnitude of the displacement is 2 meter and its direction is also along the positive direction because direction is same. Am I right? I have the origin. This is x. Here also direction is same. This is same direction. This is also same direction. The moment the ball bounced back, if something happened, the ball was thrown back here. When it crosses here, then the direction reverses. You got it? Till then, because from the 0, all directions are same. When the ball comes back, then the direction changes. Okay, so that they all explained that also. So this is okay. If the object now moves to 1 instead of 4, if it moves to 1, that means what? Now the object has moved from here to x equal to 1. Oh, sorry, x equal to 1. Now what will be the direction? Tell me.
-1.
Correct. It's a reverse direction. This was the same direction. From 0, this was the direction that was going on. Now it is going opposite towards 0. It is going towards 0. All this one away from the 0. You got it? So that's what I was mentioning. If the object now moves to x1, then the distance travelled, okay, is increased to 4 plus 3. Am I right? Because it's a 4. From here it went to 3. Okay, so 4 plus 3, that's equal to 7. Clear? You got it? Because see, what happened? It starts from the final position was x4 meter, okay, yeah, so then 4 plus 3, that makes it 7, correct, because already we got it now, 6, so what it was saying, tell me how much, so this has gone from here to here, that is 3, then
That is 1.
1,
4.
you did some mistake, so this is 3, and then 1, and from there again to
1.
1.
3.
3. So how much? Tell me.
So 3 plus 1 plus 3. That is
7. That's what they written. Okay, 4 plus 3. Initially it was 3 plus 1, that is 4. Now 4 plus 3, that makes it 7. So that's what, this is a path length. Okay, while the magnitude of the displacement, now what happened? This is x, see, from the directions we can say, this is x1, na? If you remember, x2 minus x1, correct? So here, this is our x2 final, this is the final position. And this is our initial position. So what is the difference? x2 minus x1 is?
1.
Minus 1.
But x1 is smaller. Oh, that is 2. Right?
Okay, so minus 1, that itself says the sign direction is opposite. Okay, the direction will be now towards the negative x-axis. Okay, clear? So this is what all about your displacement and path length. Okay, and then we will see 2 more quantities. So once you have, so now remember, in all these discussions, we have used only the distance travelled. But there is another one important,
Time.
important dimension which you are not considering at all. That is the time. Now let us bring in time. What is the time taken? Okay, so then what happened? So now we'll put up the same question. Going to drop the ball. Okay, so the drop the ball is, I take the second case. First case and the second case what I draw. I am going to drop the ball. The ball moved from x1 to x2. Okay. Now, I am going to drop the ball, but in between for some time, I am going to hold the ball for some time and then I drop it. Initial position and the final position, vectors are same. I mean, initial vector, final vector are same, but the time taken is going to be different. Okay, so they both are not actually same. Okay, so then it comes, we have the quantity, what we call as, I could have written here itself. Okay, so next quantity what we are going to see is velocity, or what they call it is the average velocity. Yes, the average velocity is the correct word. Average velocity. So the average velocity is, you don't bother about what happened in between. You take at the time, means initial, this is the initial position, x1, and the final position is x2. It has taken some time. You never know what all happened in between. You hold the ball, or how long you are holding the ball, nothing. This is the initial position vector, the final position vector. The difference will give you what? No, initial position vector, the final position vector. Difference? Displacement, yes. So now what happens? You take the displacement. So you know this is how much the ball has displaced. But the time can be different, right? So then that displacement divided by the time taken. Okay, so that's what you call as your average velocity. What is that? What's the average velocity?
Displacement.
Yes, displacement divided by time. Okay, so what is a symbol? If you remember, we wrote it x2 vector minus x1 vector. The time, you remember, initially it was t1 and t2, right? So t2 minus t1. This is a scalar quantity. So this will be what? Delta x vector divided by delta t. That's the time. Okay. So can you tell me velocity, average velocity is a vector quantity or scalar quantity?
Vector.
Why?
Because it has direction.
Yes, it has a direction. Displacement has a direction, right? So the V average, let me call it as V average. What the symbol they have? Okay, they symbol VAV, VAV, and it has a direction vector. Okay, so this is what you call as your average velocity. Okay, can you tell me what's the dimension of average velocity?
L1 M0 T1.
Sure, tell me.
L1 M0 T1.
L1 M0
T1.
T1.
Because only for acceleration it will be T2, but for velocity it is only one time.
1 or minus 1?
Oh, minus 1, it's divided.
Okay. Don't do this mistake. Okay. So that's what your velocity is. Example. Okay. So they give an example. Let us do the example. So it is simple, easy to understand. What the example they given is, if the positions of an object are, okay, so what they given is, if the positions of the object are x1 equal to, what they given, or okay, x equal to, let me take x and time t. I can draw na? So what they going, x is equal to 2 meter at time t equal to 0. Okay, or you can throw it up or whatever. And the x became 4 meter at time in 1 minute. 1 minute. Got it? So what it is? So the body has moved in a straight line from 2 meter to 4 meter in 1 minute. Okay, you are starting your clock when it was at 2 meter and you saw it reached to 4 when the clock exactly completed 1 minute. Okay, so now the question is, what should be the average velocity it has traveled during this duration of 1 minute? I told you simple. What is you have to make out the, okay, then the direction. Okay, so this will be what? Let me define the direction as plus. Plus, I am taking on the positive direction. Okay, so positive direction I am taking. So then what happened? So we have our magnitude of, I am going to write magnitude. Okay, direction we know because it's one dimension. Na? So let us come to the direction again. So what it will be? Tell me your x2 magnitude. This is the magnitude, right? Will be equal to how much? 4. Correct? x1 magnitude will be 2. So the displacement, okay, they both are in the same x. Okay, what will be your displacement? Magnitude of displacement. Okay, so let me write out a magnitude of velocity VAV. Okay, that will be the magnitude of displacement. What is the x2 minus x1? 2 minus x1 divided by t2 minus t1 will be how much? 4 minus 2 divided by 1, 1 minus 0, right? That is equal to 2 meter per minute. That is the magnitude of the velocity. Okay, now the direction is what?
That should be the same direction as around.
Correct. So suppose I put it in x-axis. You have a direction for x-axis. What was that? Remember? What is the unit vector along x-axis? Yes. So if you want to write down the velocity, so then here, if I want to write the velocity in a vector notation, all simple is your average velocity will be 2I cap. That's it. Okay. And it's along the x-axis. Okay. So suppose if it comes in negative, then become minus. There it comes. But here is okay, velocity we are moving in the positive direction. Okay. Cool. So now we got, this is the way the vector notation. Remember? So when since it is one dimension, we have only I cap. If it's a two dimension, then plus j cap. Then you have to see what happened. If you remember, when I say two dimension, okay, then you resolve this into two. I cap, j cap. Correct? So then you have another one component of j cap. In a three dimension, that's a space. Cap and z cap also will come. Sorry, k cap. K cap. Okay? Cool. And this what? And now we are going to do another one. So this is the average velocity. So we got average velocity equal displacement by time. Similarly, you can have something else also. No? One more, the path length. Okay, the path length by time also can come. What's the actual? That is the distance is actually traveled. You got it? So, and that will be a scalar or a vector?
That will be scalar. Right?
Correct, because path length is a scalar. Okay, so when you do that, that you call as your average. Okay, let me write it down here.
Average speed.
Average speed, yes, correct. So it's VAV, no arrows. Will be what? Path length by time. Okay, so that's what your, and again the dimension of average speed will be same, right, as a velocity. T minus 1. Okay, so total path length traveled during the time interval over which the average speed is being calculated. Okay, so yeah, remember, if you when you go back to average velocity, when I take out the case of a ball, I drop the ball and it is the time taken, and drop the ball, I hold the ball in, caught the ball in between, then I dropped. Time taken is longer. Okay, the first case, the average velocity is high. Second case, the average velocity is low, less, because the time taken is larger, division, na? Okay, and now I put a third case, somewhat you think there was, when the ball came, I put a plate down here. So the ball hit the plate and then went bounce back and then I leave it.
Both will be increasing.
Yeah, here the path length is also increasing, but when I say the velocity, it doesn't matter. Okay, so velocity doesn't matter because velocity changes. For the displacement, it doesn't matter. The velocity will be different because the time taken are different. But the displacement is going to be same in all cases. But now when the path length when you calculate for here, this is going, average speed is going to be different compared to the velocity. Okay, so it is not always, why this is important is it apparently looks your average velocity. When you take the magnitude of the average velocity is the average speed, but that is not true. Got it? So the magnitude of average velocity and the magnitude of average speed, average speed doesn't have magnitude because scalar quantity. So the magnitude of average velocity and the average speed not necessarily to be equal always. Okay? Got it? Okay. So now, so this is average velocity and average speed. Now there is something what we saw in the earlier class, that's when you are doing this calculus, differential calculus. Okay, there I was doing the same thing. If you remember, I took a line, distance and time, I put a curve and then draw a slope. You remember in the earlier class what I did was, in fact I was not knowing that you will have it in this chapter. So we draw a curve something like this, take 2 points, correct? And then what we did, we found the slope of this line, correct? So what was the slope of this line? You remember? Suppose if I call this as, suppose this I am going to call it as t and x. Okay, so this point will be what? x1, y1, t1. Sorry, t1, x1. Am I right? We will see it in the next class. Graphical representation of all those things. I want to just doing that because this we saw it in the previous class. Okay, so when you take a slope of it, slope of the line. What is slope of the line? M equal to y2 minus
t2 minus t1 divided by x2.
Sure. Here your y is x, na? So x2 minus x1 divided by t2 minus t1. That's nothing but the magnitude of your velocity. Am I right? Slope is the magnitude of the velocity. That's why I said, right? So this is nothing, that's what we did, na? The velocity. You remember? So VAV is this one. Now, when we brought a differential calculus, what we did, we call this as delta t. Then we call delta x. So then we tried to reduce delta x smaller at some point of 0. So what I want to say is the slope, the moment if I write your y-axis as a distance, a displacement, whatever, and x-axis as t, then the slope becomes velocity. Isn't it? This is a slope. The slope becomes velocity. Now if you remember, when I take the differential calculus, when I make this delta t tends to 0, this was what we did, delta x by delta t. When delta t becomes 0, right, this becomes dy by dx. There in case delta x becomes 0, it becomes dy by dx. That's a differential, right? Same way we can do here. So, and that is what we call as, that what we said there is, that is the slope of the tangent drawn at that point. Okay, now if you think, now if you see, so that's what happened, you had a axis y and x, and then you had some point and you draw a slope to the point. That's what a differential is. Slope of the tangent. Okay, now in the place of x, you put time. In the place of y, you put displacement. Then the slope is a velocity. Okay, so when that velocity, when you draw the same way, from a point you draw a tangent line. Okay, so that will be differential. Am I right? That's what we saw. You remember, I want to explain you again. Okay, that's a differential. So derivative. Okay, and that is what we call slope of the tangent at the point. The moment your y-axis is a displacement and your x-axis is your t, then the slope is nothing but the velocity. Correct? So now, when I put again for that curve, when I draw the tangent line, and when the slope of the tangent line is a velocity at that x. I will explain you again. See, this is, well, that will be very interesting way to understand your, from the, this is how the differential calculus and these all are connected. So what we had is, we had x, am I right? And we had y here. So we draw a curve something like this, and then we took a point, okay, and at that point we draw a slope sorry, tangent. Oops, sorry, I draw the point in a different place. So first I should draw the straight line, and let this be this is the tangent point. Let me call it as x0. Okay. So then, if you remember what we said, the slope of this line is what? Dy by dx at x equal to x0. Correct? So now this is what we did, right? How we got it? Because we took the line which is passing through the point at 2 points, then slowly reduces delta x equal to 0. So then we got a differential. Okay. Now let us see. I am going to change the axis. In the place of x, I am going to put it time. So how do you want to represent time? As t? Let me write this as t. So then this becomes t0. Correct? And this becomes dy, all x becomes t. Am I right? Dy by dt, and this is t equal to t0. Correct? And I am going to replace your y with the displacement, that position vector x1, x2, what we did. So let me write it as x there. Okay, the x is not your x-axis. Or if you want to confuse, let us call it as s. Okay, very good. Let us call it as s. I am going to call this as s. Okay, so this becomes, then this becomes ds by dt. Now you tell me, what is ds by dt?
Velocity.
Yes, velocity, we said that, right? Now, can you tell me, that is delta. If I draw the same thing, if you remember, if I draw it at some point, if it intersects somewhere else like this, sorry, the straight line is not straight. No more rectilinear motion. Okay. So now what happened, if you remember, we took these 2 points. Remember, that's how we did it, right? So we took this point as x1, and this we took it as delta x, right? Here this will become delta t.
Okay.
Am I right? So then what happened? So here, so this will corresponds to delta s. Okay, the slope is what? y2 minus y1 divided by x2 minus x1, right? So slope will be what? Tell me. Slope will be?
Delta t minus
Yeah.
delta t minus delta.
What is this point? Tell me.
Oh,
This point is t0 plus delta t, comma.
That won't be t0, right? This will be t0. Oh, plus delta t.
Right? So this will be let s0 into s0 plus delta s. So this will be s0 plus delta s. So this will be what? t0 comma s0. Correct? Slope is what? y2 minus y1 divided by x2 minus x1. Correct? So that y2 is what? s0 plus delta s minus y1 is s0 divided by x2 is t0 plus delta t minus t0, that will be equal to delta s by delta t, and that's nothing but your average velocity. That's what we did. You got it? At the 2 point, this is the initial position. This is the position at t0. This is the position as delta t plus delta t. So that's what your average velocity is. Once you put this as t2, that's what you get average velocity. You got it? And now you see, now when I make this delta t smaller and smaller, when delta t approaches 0, it becomes a tangent. So then it gives you the velocity at t0. Correct? Earlier we said average velocity from t0 to delta t, this is the velocity. The moment I make delta t become 0, when it becomes a derivative, then it gives the velocity at t0. That's what we call as a instantaneous velocity at a time t0. Every time. So instantaneous velocity is the next time what we do. That is the fifth one is that's what ds by dx. Sorry, dt. You are right. Yes, ds by dt. So this is a vector. Okay, so this is what they written as instantaneous velocity. Okay, and okay, in the same way the symbol here, okay, in your book they have written delta x. So I wrote it as delta s because we got confused with the x-axis and y-axis. Okay, so if you in a book they write as delta x, you can do it. Usually distance they show by delta x or delta x also, because position vectors is always shown as x. And the reason is why they said it as x is we are dealing it one dimension. Here I draw the two dimension. When it is one dimension, I am going to take in the x-axis, right? So other thing is a time. So when we see the graphical representation, it becomes very clear. So that's why I plot the graph. Anyway, they are showing it in the next lecture. I will show the graphical representation, more detailed graphical representation of all these quantities. Okay, so this is the instantaneous velocity. So if you want to write it further, you know that, na? It's what? Limit delta t tends to 0. So what will be? Tell me. Delta s by delta t. You can do this way. Correct? Yeah. So this is what they call as here. Is this a vector?
Yes.
Yes, correct. Because this one is a vector, right? So this will be, this represents just a v, not a v. Okay. The same way you can do your instantaneous speed also. I'm not going to tell you. Same way you can do now. In the place of displacement, you write a distance. The path length. Sorry, the path length. So when you put the path length, of course, again there also you can have instantaneous speed. So that's again a scalar quantity. Okay, so that's what your instantaneous speed is. Okay, so I'm not going to tell that you can. The instantaneous speed is the speed of an object at a given instant of time t. Okay, it is a limiting value of the average speed of the object taken over a small interval of time delta t. Correct, when delta t becomes 0. This is an interesting point. See, your instantaneous speed, what I said earlier when I said the average velocity and average speed, okay, what I told you is it appears that average, the magnitude of the average velocity will be the average speed. That is not correct. But now you take about instantaneous velocity and instantaneous speed.
In that one, it will be
Equal, because at every point, I see all I'm saying is the position. At that point, what is the, at that x value, what is the speed? If you give the direction, then it becomes velocity. If you say only the speed, it becomes a instantaneous speed. What I said?
You said if you give the speed, you said.
If I give only the position, or okay, the path length, the distance, then it becomes the instantaneous speed. Okay, so it doesn't matter. So in that case, what happened? Instantaneous velocity, if it is the magnitude of the instantaneous velocity, that is nothing but instantaneous speed, but that is not true for your average velocity and average speed. You should remember it. Okay, so they returns. The path length will be equal to the magnitude of the displacement. Okay, and so the instantaneous speed will always be equal to the magnitude of the instantaneous velocity of the object. Okay, just remove the direction. That's it. Okay, and there are some points you have to remember for a uniform rectilinear motion. What is uniform rectilinear motion? Equal. It travels equal distance in equal interval of time. Uniform means it travels equal distance, equal interval of time. I am dropping a stone. Is it uniform?
Yes.
Is it so? It travels equal distance?
Distance?
When I drop a stone.
Oh, the distance increases, but...
Okay. Let us drop a stone from third story. The time taken for the stone to cross the second story and the bottom, will that be same?
Okay, no, it will be different.
It will be different because there it will be slower.
Ah.
As it goes down, it becomes faster. Why? There is acceleration. That's what acceleration due to gravity.
Ah.
Once the acceleration due to gravity, it's not going to be uniform motion. It's a non-uniform motion.
Ah.
Okay. For uniform rectilinear motion, when it is a constant velocity, for an object moving with constant velocity, okay, there is no acceleration. That is for an object with a constant velocity along a straight line. Okay, so remember, you are traveling in a car at a constant speed in a straight line. The average and the instantaneous velocities are equal. Correct? Is that right?
Average and-
Think of. The average velocity is what? Take two time difference.
Ah.
Okay, take two different time. Take out the position
Ah.
and take out the displacement.
Ah.
Divide by the time taken.
Ah.
It's going to be same.
Okay. Ah.
You got it? Because it travels equal distance at equal interval of time. You take the difference wherever.
Ah.
Or take the distance time scale time smaller. It's going to be same.
Ah.
Okay, as you make your delta t smaller and smaller, it's going to be same only. It's not going to change. So your average velocity and instantaneous velocity is going to be same in case of uniform motion. Uniform rectilinear motion. Okay. The average and instantaneous velocity are equal. The average and instantaneous speeds are the same and are equal to the magnitude of the velocity. Of course, the speed also going to be same. Okay, and that will be what? You are a rectilinear straight line you are going. You are not coming back. You are not stopping. As I said, I am going to stop. You are going on a constant velocity. So there what happened? Your path length is also going to be not going to affected. Path length is just the magnitude of your displacement. Okay, so therefore the magnitude of displacement, time, everything is taken same. So your instantaneous velocity, what is the average speed and the instantaneous speed are going to be same, and they both will be simply equal to the magnitude of the instantaneous velocity or average velocity. Doesn't matter, they both are going to be same. Okay, so this is for a uniform rectilinear motion. You got it clear? And now let us go for a non-uniform rectilinear motion. That's what you're dropping the stone. Speed up. Okay, that is non-uniform. So there what happened? There it's going to be different. Because your average velocity and instantaneous velocity is going to be different. Your instantaneous velocity initially it will be slower. As it reaches the ground, it's going to become faster. Okay, so when I take the total velocity, that's going to be different. The distance also. There what happened? In that case, the average and the instantaneous velocities are different. Correct? When I drop the stone, initially it was slow. Then became fast. Now we take the average velocity. That will be different from the velocities what I calculated. Am I right? So that will be different. So of course this is also same. The average and the instantaneous speed is also going to be different. Okay, the same speed is also going to be different. Okay. The average speed will be different from the magnitude of the average velocity. Can you tell me why? The average speed, let us drop the stone. Okay, it's having a speed. The average speed will be different from the magnitude of the average velocity. When I put the example of dropping the stone, that is a special case where your average speed and average velocity will be same in magnitude. Correct? Because what happened? You are taking the path length is straight. Same, the path length is equal to the magnitude of the displacement. Okay, now we take the case of where I put the second case, where I hold the one. Okay, so then it becomes, that's also non-uniform. Am I right? Because speed up, then it says a zero, it took rest, and it's non-uniform motion. There it won't be same. That's what they written. The average speed will be different from the magnitude of the average velocity. Okay, so these are the important points you should remember when you are dealing with the motion of the object. Okay, and till now we are dealing with the motion object in one dimension. Okay, that is a rectilinear motion. Okay, so first we will derive all the equations of motions, everything in a rectilinear case, and then we will come to motion in a plane. Okay, so that's why we will maintain the vector symbol. So it will be easier for us to connect in the motion in the plane. Okay, so tomorrow we will see the graphical representation of this whole quantities. Okay, and you will see that what do we mean by when I plot. See, when I plot this, for example, there's a uniform motion. Uniform motion is constant velocity. It will be a straight line, and the area under 2 points, that area will become the average velocity. Okay, so all those things we will see it tomorrow. Okay.